Here are our solutions to homework set number 11 for ECE 376 Embedded Systems. This homework set looks at Z-transforms and digital filters. Basically anything you can do in hardware, you can do in software, including designing filters. Now the first problem actually looks at analog, more of a hardware type of filter. If I have a filter in S, what that means is a differential equation. There's my mouse. So this is the relationship between x and y. This is your gain g of s. It's essentially the gain that depends upon frequency. What this represents is a differential equation. If I cross multiply and then note that s means derivative, then what I get is the second derivative of y plus 10 times the first derivative plus 30 times y is 3 times the derivative of x plus 6x. So this differential equation is the same thing as that transfer function. Just a different way of writing it. So anytime you see a transfer function in S, think differential equation. The reason we do that is it makes analysis when you have sinusoidal inputs much easier. So for example, if my input is 6 plus 5 sine 4t, use superposition. Treat that as two separate problems. What superposition says is for linear systems, f of a plus b is equal to f of a plus f of b. You can treat this as two separate problems. The input is 6, the input is sine 5 sine 4t. Solve those separately, add them up, I get the total answer. So the first part, when x equals 6, the phasor representation is just 6. The frequency is 0. This is 6 e to the 0t. Laplace transforms assumes everything is in the form of e to the st, in this case s equals 0. This is the gain everywhere. All I care about is what's the gain at s equals 0, times the input at that frequency. Multiply it all out, I get a number, 1.2, which means 1.2. Now the second part. When x is 5 sine 4t, s is j4. The input is 0 minus j5. In phasors, the real part is cosine, minus j is sine, so this represents 5 sine of 4t. This is the gain everywhere. All I care about is what's the gain at s equals j4, times the input of that frequency. Multiply it all out, I get a complex number, and what that means is the real part's cosine, minus j is sine. The total answer is then the sum of the two, your DC term plus your AC term. So there's y of t. That's in the S-plane. In the Z-plane, it's really the same thing. If I have a transfer function in Z, that represents a difference equation, different than a differential equation. To get that, cross multiply, multiply out. Note that zy means the next value of y. So z squared is y 2 samples in the future. That's a z. Zy is 1 sample in the future. Y is just y. Zx is x 1 sample in the future, and x. So this is the difference equation that corresponds to that transfer function. On part B, if the input is a DC and an AC term, same procedure. Use superposition, treat that as two separate problems. When the input is 6, s equals 0. Z is e to the st. That's the connection between the S-plane and Z-plane. When s equals 0, z equals 1. This is the gain everywhere. Analyze that z equals 1 times the input, and I get 60. When the input is 5 sine of 4t, x is 0 minus j5. Again, just like before, real part's cosine minus j is sine. S equals j4. Z is e to the st. Analyze, I get a complex number. The real part is cosine minus j is sine. The total answer then is your DC plus AC. So there's y of t. Problem 3. Convert from the S-plane to the Z-plane. This is something that I prefer doing. I am semi-comfortable in the S-plane. Z-plane I find kind of weird. So what I like doing is designing filters in the S-plane. Those I kind of understand. To program them, I go to the Z-plane. The connection between the S-plane and the Z-plane is z is e to the st. I have to know the sampling rate. I have to know t. If I know it, in this case t is 0.01, I can convert. If s is minus 5, z is 0.9512, minus 10, minus 20. So my filter has 3 poles in the S-plane, my filter has 3 poles in the z-plane. This is how the first pole converts, second pole, third pole. And there's other ways of doing it. I prefer the e to the st approach because to me it makes more sense. I've got 3 poles s-plane, 3 poles z-plane, and this is how it converts, e to the st. To find k, match the gain at some frequency. So if I pick DC, the DC gain is 2, pick k to make the DC gain 2. Again, at DC, s equals 0, z is e to the st, so z is 1. Solve for k to make this match up, and you get k is 0.0016. So there's g of z. To check if this is correct, plot the gain versus frequency, g of s versus g of z. In MATLAB, I'm going to plot from 0 to 30 radians per second. S is j omega, and here's g of s. Almost the way you write it. You just have to be careful. These are dot slashes because I don't want to do matrix divide. I want to do element by element division. And I need to have these extra parentheses, so all these are in the denominator. That's g of s. For g of z, there's my sampling rate. Z is e to the st. That's the g of z I just calculated. And plot the two together. And here I'm going to plot frequency versus g of s in blue, frequency versus g of z in red, and I'm going to shift gz by 0.01, just so you can tell the difference. So here you can see the blue line, that's g of s, the red line, g of z. Same gain versus frequency, it's the same filter. Doesn't really matter how you implement it, it's the same filter. That works with complex numbers as well. Take another g of s, I've got 1, 0, 2 poles, convert to the z-plane. The 0 converts as e to the st, pole converts, second pole converts. So that means I've got 1, 0, this term right here. I've got 2 poles. I can't set the DC gain because the DC this equals 0, so I get 0 equals k times 0, solve for k. That doesn't really help. Pick some other frequency. I chose 10 radians per second. Doesn't really matter what frequency you pick. At 10 radians per second, this has a magnitude of 4.94. At that same frequency, pick k to have the same magnitude. That gives me k is 0.2908, so there's g of z. To check, plot the gain versus frequency. So just like before, frequency goes from 0 to 20 radians per second. Here's g of s, t, z is e to the st, here's g of z, plot the two together. Shifting g of z by 0.01, just so you can see it. And you can see the two curves. There's your g of s in red, in blue, g of z in red. Same gain versus frequency, same filter. Problem 5. Write a C program to implement this filter. Now this is why we like digital filters. They're really easy to implement. The trick is multiply everything out, cross multiply, find the difference equation, shift everything so it's causal, solve for y of k, and that's basically your program. In fact, you can kind of see this by inspection. The denominator polynomial appears here. The numerator polynomial appears here. The denominator polynomial has got a sign flip because I cross multiply and bring it right. So you can almost write the equation, write the program by inspection. The code is I have to remember the input 1 sample ago, 2 samples ago. Remember the output 1 sample ago, 2 samples ago, using variables that C will accept. Then that right there is really your program. Plus, presumably, I have to output the data because I computed this filter for some reason. And important, I've got to wait 10 milliseconds. That's t. If I change the sampling rate, I change the filter. So you got to have the correct sampling rate. Number 6. This is looking at some applications of digital filters. In the previous homework set, we had an ultrasonic rain sensor that I could measure distance. I collected 1,000 data points, and here's what it looks like. This is a block at about 100 millimeters away, the range data. It's usually pretty consistent, occasionally coupled glitches, jump discontinuities. If I look at all the data, it's going to have noise on it. What I'm going to do is take the data between 350 and 850. That looked like pretty good data. If I do that, here's what the data looks like. Now, there's a couple jump discontinuities in there. If I find the mean, standard deviation, these are going to mess up the data. If I do that in 7, just take the data as is, find the mean, standard deviation, confidence interval. With 500 data points, the t-value for 5% tails is 1.648. So go left and right, 1.648 standard deviations. And there's my confidence interval. 90% of the data should wind up in this range. And it's fairly wide. The reason it's wide are these few data points causing the glitch. That increases the standard deviation, which messes up my measurements. If I could get rid of these, I'd get a smaller standard deviation, a better measurement. So one way to get rid of them is a median filter. What a median filter does is if I have 3 data points, I'll sort them and take the middle value. So what that kind of does, if I have a glitch like this, what I'm going to do is for these three points, take the middle value, that's right here. For those 3, I'll take this value. These 3, I'll take this value. These 3, take this value. It helps get rid of jump discontinuities. So if I do that, take the data, take 3 points, the previous point, current point, next point, sort it, take the middle value. That's the median filter. Call that my new data sets. Here's what it looks like. It's better. I still have a couple jump discontinuities in there. So what I'm going to do is manually go into the data and fix these points. Get rid of them, kind of put them into here. That's manually getting rid of the glitches. Kind of easy to do by hand, hard to do in software. But if I just hard code it, get rid of these glitches, then look at the data, here's what it looks like. And now I've got a much tighter band. If I find the mean and standard deviation, the standard deviation is much, much smaller. My confidence interval then says I'm somewhere between 109.22 and 109.175-ish. Much tighter band. That's what a median filter does for you. There's still noise in the data. Can I get rid of the noise? Well, that's the next problem. Problem number 9 says, let's take the data and average it. If I average the last 5 data points, averaging helps get rid of the noise. So here's a program that does that. For all the data, I'm going to take the average of 5 data points, and that's my filter data. If I do that, my standard deviation gets smaller. Before, it was 0.014. Now it is 0.0097, a little bit smaller. My data looks like this. Again, not quite as noisy. That's what averaging does. Gets rid of the high frequency noise. Smaller standard deviation means a tighter confidence interval. Now you can do better than averaging 5 data points. This is where the Z-transforms really shines. If I want to run it through a second order Butterworth low-pass filter with a corner at 2 radians per second, actually 2 squared to 2 radians per second, that's what it looks like in the S-plane. Where that comes from, stay tuned. When you take electronics too, you'll get that. For now, just take that as granted. Here's the filter in the S-plane. Convert to the Z-plane with t is 10 milliseconds. Here's the same filter. This second program, this just says going to spin through my data. The current output is 1.96 times the previous output, minus 0.96 2 samples ago, plus 0.0008 times the input 2 samples ago. Spin through the data, run it through that filter, and now the standard deviation drops to 0.005, much, much smaller. If I plot the data, it looks much cleaner. Basically, you can do a whole lot better than averaging, but to figure that out, you have to go through the point where you have Laplace transforms, filters in the S-plane, S to Z conversion, digital filter. Took a while to get here. Once you get here, I can filter my data and get a much better measurement. So that is homework set number 11 for ECE 376. This is one of the reasons we study Z-transforms. If you want to filter some data on a microprocessor, you really should be using Z-transforms. You have a difference equation, you've got data at discrete time points. Difference equations are much easier to implement in code. And it's identical, equivalent to the S-plane, but z-plane is how you implement it. For me, s-plane is how I analyze it. Homework set number 11 for 376.